Our last example has to do with the gravitational force and work. So suppose you are in a rocket ship on a journey to the furthest reaches of the universe. The force of gravity between two masses is given by F equals G, the gravitational constant. That's not the acceleration due to gravity on Earth, which is 9.8 meters per second squared. This is the universal gravitational constant, 6.67 times 10 to the minus 11 Newton meters squared per kilogram. So it's equal to that gravitational constant times the product of the two masses, and then divided by the square of the distance between them, r squared. So we would say that the gravitational force on two objects is proportional to the product of the masses and inversely proportional to the distance between them squared. So understand that the gravitational force exists between all objects. Any two objects are going to feel a gravitational force between them. There's going to be an attraction between those two objects due to the gravitational force. Now, normally, you don't see the effects of this gravitational force between two random objects because the masses of those two objects are quite small, and so because of the constant g and the division of the square of the distance between those two objects, that's going to make the force very, very small. So if you have two people standing relatively close together, maybe a meter apart, they're not going to feel the gravitational force between them because their masses are too small. But when you have a large object, like a planet, then you're going to be able to feel the gravitational force between that planet and other objects. It's because the mass of that planet is going to be very large and it's going to overcome that universal gravitational constant G. So what we would like to do is, if we were to start the rocket at the surface of the Earth, find out how much work it takes for that rocket to fly to an altitude of 1,000 meters, and then 1,000,000 meters, and then how much work it takes to escape Earth's gravity. So let's think about problem A for a second. How much work is it going to take to fly to an altitude of 1,000 meters? Well, work is going to be the sum of force times distance. But in this case, work is going to be the integral of force times distance. So we're going to integrate from the surface of the Earth, which is the radius r, to the radius r plus 1,000 meters. And we're going to integrate that gravitational force. So this isn't actually the gravitational force. The gravitational force is going to be the negative of this. That's the force that gravity is exerting between two objects. Okay, but this is the force that opposes gravity. Okay, that's why we're using a positive there. So this is going to be gravity times the mass of the Earth. I'll call that m sub e. And then the mass of the rocket, I'll call that little m. And then we're going to divide that by the distance between them, r squared dr. So the distance between the two objects, or r, is also going to characterize our height of the rocket above the Earth. Okay, so we're going to do that integral. The integral of 1 over r squared is going to be minus 1 over r. And so we have capital G, little m, e, little m. We're going to evaluate that between r and r plus 1,000. So this ends up being g, mass of the Earth, little m, times, and then because there's a negative sign there, I'm going to do these in reverse. 1 over r minus 1 over r plus 1,000. Now all that's left is to plug in all of the different constants, and we're going to get 9,815 joules. That's how much it's going to take to propel the rocket 1,000 meters above the Earth. Ooh, I want to apologize right there. It's 9,815 times the mass of the rocket, joules. Now let's go to 1,000,000 meters. So again, we're going to do the work is going to be the integral from radius of the Earth to the radius of the Earth plus 1,000,000. And then we're going to integrate gravitational constant m sub e, the mass of the Earth, mass of the rocket, r squared dr. And so again, that antiderivative isn't going to change. Gravitational constant times mass of the Earth times little m over r. But now I'm going to evaluate between r and r plus 1,000,000. So in fact, we get g me little m times 1 over r minus 1 over r plus 2, 3, 4, 5, 6, 1,000,000. And in fact, this is going to be plugging in all the constants, 8,484,743 times the mass of the rocket, joules. So to get to 1,000,000 is a lot more, okay, 1,000,000 meters above the Earth. But finally, we want to answer the question, what if we want to escape Earth's gravity? What would we have to do? Well, then our work would actually be the integral from r. And if we want to completely escape Earth's gravity, there would have to be an infinite distance between the rocket and the Earth. So we would actually be integrating to the radius of the Earth plus infinity in essence. Or we could just say infinity. Well, we're going to integrate again the gravitational force, or the force that will oppose the gravitational force. And this is an improper integral, so we're going to need to do the limit as, well, I'll call it h goes to infinity, h being like the height above the Earth. So we're going to integrate from r to h, g me little m over r squared dr. We've done this so many times that I can write down what that limit is going to be. So limit is h goes to infinity, g me m times 1 over r minus 1 over h. Now, if we take the limit as h goes to infinity, this term, as you can see, is going to go to 0. It's getting smaller and smaller. And so what's left is the limit. Nope, there's no more limit. What's left is capital G, mass of the Earth, m over the radius of the Earth. And what's important there is that is a finite amount. Now, it's a large amount. That's going to be 62,532,559 times the mass of the rocket, joules. But nevertheless, that is a finite amount. And that means that it only takes a finite amount of energy for a rocket to be propelled far enough to escape Earth's gravity.